Good morning, everyone. I hope that you had a great weekend. I know today is Wednesday. So, today we're going to go over the beginning of 16.2 and we're going to go over heat and thermodynamics. And I wanted to start off with the example that they start off in the section. It says to bake cookies, you put cookie dough on a baking sheet and pop it into the oven. When the timer goes off, you use your oven mitts to pull out the baking sheet. Why isn't your bare arm burnt by the air in the oven? One reason is why. Okay, so when we are baking our cookies, and I know so many of you have been baking cookies because I know I've been baking a lot of cookies during our quarantine. But so, why is it if I put my arm in that oven, why is my arm not burning right away? And the reasoning why is because that air is not a good conductor of heat. So, if we jump into this slide right here, it says conduction is the transfer of thermal energy with no overall transfer of matter. So we're not transferring matter back and forth at all. Conduction occurs when two materials are touching or come in contact with one another. So conduction in gases are going to be slower than in liquids and solids. Because if you remember section 16.1, gases, their particles and are going to collide less because their particles aren't close together. Remember, they're kind of spread out, colliding into one of each other. So they don't have as much contact. So it's going to heat slower due to the particles not touching as much. Liquids and solids, they're kind of closer together, so they're going to be bouncing back and forth so it can conduct heat or conduct thermal energy better. So conduction in metals. In metals, conduction is going to be faster because some electrons are freely to move. If we look back at the periodic table, when we were talking about electrons, they had electrons that could move all over the place. Well, that's why they're going to be able to heat up quicker. And in the book, it talks about thermal conductors. Let me move my thing up here. A thermal conductor is a material that conducts thermal energy well. I have a bunch of examples for you that you can see which are good conductors. Your good conductors are going to be metals. Metals are great conductors for this. So in the book, it talks about a thermal conductor, and it talks about tile floor versus wooden floor. And what it wants you to know is that thermal energy doesn't always have to be hot. So when we think of a conductor, we always think that a temperature difference that's going to be hot. Like we touch a metal pan, ow, it's going to be hot. That is not always the case. Sometimes you can look at it as cool. So in the book on page 480, it brings out an example of a thermal conductor, and thermal conductor is wooden floors versus tile floor. And it says both floors are at room temperature, but the tile feels colder on your feet because it's a better conductor and transfer thermal energy rapidly away from your skin. Remember, hot is going to go to cold, right? So it is going to conduct that heat. It's going to grab that heat from your feet and it's going to pull it into the cold tiles. That is why it feels that tile is colder on your feet than on a wooden floor. So if you have wooden floors and tile in your house, check it out. Tell me which one feels cooler to you. So thermal conductors, once again, is just anything that's going to be able to conduct thermal energy well. Insulators. All right. So an insulator is the complete opposite of thermal conductor. It's a material that conducts thermal energy poorly. and that is going to be a thermal insulator. I have plenty of examples right there for you of different kinds of insulators. And then on page 480, again, it gives you an example of air. And it says, air is a very good insulator. So it brings up these double panel windows. And so if we have these double panel windows, it's 2 windows, and in the middle is going to be air. Well, during the wintertime, it slows down that heat loss. So it's going to trap that heat into the house. And then during the summer, air is going to keep heat from coming into the house. So it's kind of insulating that house. During the wintertime, when we want to be all warm, it's going to keep heat in. And then during the summertime, when we don't want any heat into our house, it's going to keep it outside. So that's just an example of an insulator. There's plenty more examples, but I'm going over the ones that are in the book. All right, so that is conduction. Now we're going on to convection. So convection is the transfer of thermal energy when particles of a fluid move from one place to another. So convection is we're looking at the particles of the fluid move from one place to another. Remember, fluid can be gases or it can be liquids. So a convection current occurs when the fluid circulates in a loop as it's alternating, heats up, and cools down. I will give you a perfect example of this, and we're going to do this by using an oven. So remember, conduction is when 2 materials are in contact with each other. Convection is the transfer of thermal energy when particles of a fluid move from one place to another. And I'm going to give you a great example of convection and convection current in the next slide. Let's go to the next slide and then we'll talk about this. So it talks about in our book on page 481, it says, well, why do some recipes ask you to use the top rack when you're using the oven? So there's some cooking materials where they want you to use the top rack than the bottom rack. And you might be asking yourself, well, why? It's in the oven. Well, so the air at the bottom of the oven is going to heat up. If you pull open your oven, which I will show you in a little bit. I'm going to pull open my oven. Sorry if it's a little dirty. But you pull it open, your heat source is at the bottom. So you turn on the oven, that heat source is going to go on. It's going to start warming up that bottom air, right? Because it's going to come in contact with the air first. So the air at the bottom of the oven heats up. Well, what are those particles doing? The particles are going to move quicker, right? They're going to come in contact and they're going to kind of expand. Remember, when particles heat up, they're going to have a lot of kinetic energy and they're going to expand. Well, that air expanding is going to make it less dense. And when the less dense air, it's going to move up into the oven. So as that air moves up, it's going to cool, all right? And as it cools, it's going to become less dense, so that means that the particles are going to slow down and they're going to come back into contact with each other. So the air on the top of the oven is going to be it's going to be more cool than the air on the bottom. And then once that air becomes more dense again, it's going to fall and it's just going to be a current. So yes, the top of the oven is always going to be a little cooler than what the bottom of the oven is going to be. So it just goes in a current like this. It's going to do circles. Hot air speeds up the particles. They're going to expand. They're going to rise because heat is always going to rise. So because it's going to want to go into that cooler area of the oven, remember, because we could move from hot to cold. So it's going to move up, and as it moves up, it's going to become less dense, slowing down the it's going to become more dense, slowing down the particles, and then as it becomes more dense, it's going to fall again. So convection current. So convection currents can also be very important in many natural cycles. So the ocean currents, same thing. They are in a current. Weather systems happen in currents. And the movement of hot rocks in the Earth interior is also going to be due to convection currents. All right, the last one we're going to go over is radiation. So radiation is the transfer of energy by waves moving through space. All objects radiate energy. As the object's temperature increases, the rate at which as an object's temperature increases, the rate at which it radiates energy is also going to increase. So temperature is going to increase, radiation is going to increase. And it's just in wave form. So the sun and the earth, in between there's no air. So it's going to go straight to the earth. It's going to be in wave form. It's going to radiate. What I want to do is also go to my oven right now. In the book on 481, it shows you a picture of like a hot plate and the coil. If you get very close to that, it's going to be hot, right? Because your temperature is going to increase as you go closer to the oven. As you back away from that hot plate, it's going to cool down because you're not as close. So let me pause this video real quick, and then we're going to go into my oven or my stove. All right, so we have my pot, we have my stovetop here. Let me move to my next slide. All right, perfect. So, I turn on my oven. It's going to heat up. You can see the redness. That is going to be radiation. It's radiating off of my oven, okay? I put this on here. If I had water in there and my fluids, right? The fluids in there, the particles are going to be moving, going from the hot to the bottom. So hot's going to be on the bottom of the pan because that's where the heat source is. Then they're going to speed up and they're going to do convection currents, just like in the picture. Then conduction. My pan clearly is not going to have a metal handle because it's going to be extremely hot. I would burn myself. So we could use an example of a metal spoon. If I put this metal to metal and I held it there, that metal is going to heat up this metal, and that is going to be an example of conduction. Two materials hitting each other. So once again, my oven, it's going to be hot, so this is radiating off of it. It's going in waveforms. This heat is causing this fluid to have a temperature difference, causing that convection current. Hot at the bottom, particles are coming together, they're hitting each other, becoming more dense, they're going to move up to the cooler area, and it's going to keep on going and having a convection current. Then conduction is going to be metal to metal. All right, guys, that is all I have for you today. Make sure you copy these notes into your notebook or the outline that you have already done. And I also want you to do this at your house and be able to feel the differences and be able to see where radiation would come, convection would come, and where conduction would come. Remember, these three things are going to be very important when transferring thermal energy. All right? So have a great day, guys. Enjoy your day, and make sure you check out your assignment. All right? See you guys. Bye.